what I'm representing here is the work of several thousand people inside Google and our partners elsewhere. So I'm just, the tip of a very, very large iceberg here. I'm going to be talking about just some aspects of things. I couldn't possibly tell you everything that we worry about while we're trying to do these things, but I'll sort of give you some flavor for the kind of things we care about while we're constructing these very large-scale computer systems. And that subtitle is, I think, we'll come back to and touch on that. Supplying exponential growth is an interesting problem and opportunity. As an engineer, I like problems because they form good opportunities. I'm going to start with a very short video just to give you basically the essence of the talk. So let's watch that together, and then we will actually dive down into some more details.
With 7 Google products that serve over 1 billion users and dozens of products that serve over 1 million users and front-end traffic that serves millions of queries per second, Google's scale is likely no surprise. But have you ever wondered what it takes to construct Google's computing infrastructure at that scale? It starts with forecasts of how much compute, storage, and network capacity is needed by product teams across Google. The forecasts drive plans for how much supporting infrastructure to deploy. That plan initially tells us when to find power, build data centers, design and deploy networks, and establish edge network presence throughout the world. Later on, a product team decides exactly when they need additional compute, network, and storage resources. That triggers an order for hardware. Here's how that works. Our suppliers ship the parts needed to contract manufacturers who assemble them and store them in a regional warehouse for future use. Much of our hardware is custom built to our own designs, such as tensor processing units. We decide when to acquire inventory to make sure we achieve cost-optimal availability and ensure that hundreds of components from dozens of suppliers around the world come together when they are needed. Trucks, planes, trains, and pack mules take these parts to a local spoke warehouse close to our data center. Once they get there, local staff perform the install, connect the power and cooling, and then the new gear is tested automatically before it's turned over to our product teams. In the Unified Fulfillment Optimization Team, or UFO, we're automating this entire process. We're aiming to minimize Google's costs, and since we spent $30 billion on capital over the last 3 years, that's a big deal, and help ensure that Google can continue to scale. We help deliver hundreds of thousands of computers a year, and network capacity that lets us contribute 25 to 40% of the global internet user traffic, all in support of serving billions of queries a day from our users. We are software and hardware engineers, operations and machine learning researchers, analysts, and product and program managers. Come join us.
Okay, great. I'm not actually out to hire you, but I just thought it's a recruiting video we put together a while ago, 2017, actually. Bear in mind that $30 billion trailing 3-year CapEx number. We'll come back to it. But I want to start with sort of talking about what the scale of computer systems that I'm interested in, can accomplish for you. And the basic message I would offer or suspect is, I grew up using single board computers and desktops and sort of mainframes and things like that. I've got a couple lying around here. This thing's running on my Windows desktop. But that's not the scale of computer system we're interested in these days. And I'm going to argue and suggest gently, hopefully politely, that some of you might be thinking a little bit too small in terms of the scale and scope of stuff that we're trying to accomplish here. The scale comes because of the ambition. The ambition is because we want to be able to do things like this. The x-axis here is a few weeks. The y-axis is basically cloud demand, cloud data store transactions per second. The orange line is what the marketing people thought could happen if things go well. The engineering team said, yeah, we're going to play it safe, and I guess that the red line might be a worst case upside if it does take off. And the green line is the demand that was generated over a few weeks when Pokemon Go went live. You can't do this kind of thing if you're building your own data centers unless you're doing something about amortizing scale. So you want to be able to support people who have that kind of business ambition. And here's another example, just sort of to bring a couple of things through. As an experiment a couple of years ago, 4 years ago now, I guess, I ran a deliberately brute force query over a petabyte of data. That's a lot of data, right? That's 10 terabyte disk, that's 100 of them. If you do that serially, you're looking about 50 days of elapsed time, assuming you have nothing else going on. If you do them in parallel on each of the disks, you're looking about half a day of elapsed time. I'm and interested in using the building systems that allow you to do that about 100 times faster. It actually took less than 6 minutes. And in the process, it burned around about 6 days of computation time in addition to the disk access time. These are not systems you put under a desktop. These capabilities are amazing that we can deliver these both to our internal users and to outside folk via the cloud products. But we're in the business of internally of trying to make sure that people who do want to do those kinds of things can do them. So here's a picture of the kind of computer systems we build. It's that thing in the middle. It's a warehouse scale computer system, which is named after a book with the title Warehouse Scale Computing. This one happens to be in Iowa. I've actually been here. These are non-trivial in size, right? A small one, not shown here, 5 to 10 megawatts. A big one is 40 megawatts plus. There's probably about 3 of them inside that orange yellow rectangle I've drawn here. We construct our own electric substations. This is somewhere close to 0.5 gigawatt of electrical substation capacity for those of you who like electricity. And to avoid the place melting down, we have cooling towers to make sure that the heat gets sent outside rather than get stuck inside the buildings. So those are the kind of systems we're interested in trying to put together. And my job is sort of helping make sure that a fragment of this stuff gets done on time, cost effectively. So what if the systems we're interested in were not just single board machines or single servers, but the computers, all of the computers, the network fabric, the wide area network endpoints, the cooling systems that stop stuff going bad. And yes, the internet is actually made of pipes and tubes. The power systems behind them and the folk that actually run these data centers, because it turns out you need people to run around and do things and maintain them and break them. That, by the way, is a 2 megawatt generator. The size is picked because that sort of cost performance optimal point. This is all engineering, right? But thanks to hospitals, for which 2 megawatts is a useful size. So there's lots of 2 megawatt generator capacity available. We buy lots of these things. And security, right? The stuff needs to make sure we don't leak things outside. So we make sure that you have to work very hard to get into one of these buildings. And in fact, you have to work even harder to get out. They will scan you through metal detectors on the way past. There are iris readers that you have to pre-register for before you're allowed in. A single person has to go through essentially an airlock at one person at a time before you're allowed inside the building. I've been through these things. In fact, the whole warehouse scale computer. So that's sort of the unit of conversation here. By the way, no pressure. We're talking a few $100 million each. So if you're the person making the decision, should we build one of these things? Interesting choice, right? Let's spend a few $100 million or not. Should we do it now? Should we do it later? So this is the game we're trying to play. Do we make sure we have enough compute capacity to meet the needs of our external customers and our internal ones as well? So how many of these things are there? Quite a lot. This is a picture of edge point of presence location. So it's more than the data center. Some of these are sort of much smaller things. They have connectivity to the outside world. But as the video said, we generate something like 1/4 to 40% of the total internet network traffic gets sourced or sunk in our places. So we started doing things like pulling fiber. Submarine fibers had been brought into the world because it turns out there wasn't enough capacity across the Pacific to do the kind of things we needed to be able to do. Those things can sometimes take 5 to 10 years to build. So this is a game of predictions. We'll come back to that in a minute. So yes, there's lots of these things, 34 regions, the cloud regions, a couple of 100 countries and territories, complicated legal stuff, and they're all over the place, and they're breeding. More and more of the business is going out into the things that are close to customers. You want low latency access, so we're building these things that are close to our customers. We call them sort of typically colo facilities. So let's now talk about the planning process we use to make decisions about when we should or should not go construct one of those things. So how hard could this be, right? We're going to take a data center, fill it with computers. There's a few CPUs in them. There's some memory. There's some disks, a bit of disk, a bit of store SSDs for flash. But actually, it's more complicated than that, right? Turns out there's lots of different kinds of storage devices. There's lots of different kinds of accelerators, which make these things much more power effective. Networking turns out to be an interesting design space. That's my current area of work. The power and the cooling infrastructure turns out to be, there is no standardized answer because it's a function of all sorts of different choices you get to make, trading off various alternatives. And then choices about the buildings themselves. What's the right granularity for construction? Somebody has to go buy or lease land. And we worry about things like, do we have enough water capacity and sewage capacity? Fun fact, we denominate many of these things in megawatts. We'll come back to the power story later. But so I've been in conversations where people talk about how many megawatts of sewage do you need? Okay, fine, right? Because there's fairly static ratios between megawatt consumed in the data center for computers and the like. And each of these things isn't one example. The computers, the ones you buy tomorrow from Intel, are not going to be quite the same as the ones you bought yesterday, even though they might have the same part number, because they've got new firmware on them, or the IC hardware has changed just subtly. So that complicates things. There's some different price performance points and different performance behaviors. Okay, great. That's the first thing. The second thing is, as a software engineer, I mean, I'm used to dealing with things with response times in milliseconds. Microseconds if you're pushing things these days, occasionally nanoseconds. This is not the game we currently play. I mean, we're talking years, weeks, months, weeks if we're lucky, days if we're very lucky, not milliseconds. So, here's a data center in Singapore. We're now building them vertically, not just sideways. And these things don't come into existence in a hurry, right? You have to plan for these things far out. And it turns out that the variance in the time it takes to deliver them is as bad as taking a long time, right? 12 months is bad. 12 months plus or minus 9 months is very bad, because you basically have to plan for the worst case, because the downside of not having enough capacity is really bad. Okay, so let me give you a way of thinking about the whole big picture we're going to talk about here. The first is fairly simple. We just need to build a model, a forecast of how much demand there is going to be for computation cycles, networking, storage, etc. Then we have to use that to decide when to go construct buildings and get the land and lease space for them and make sure they've got enough external mains power. We then fill them over time with networks and storage. You don't want to do all at once, because that's super expensive. And if you defer and delay, then you could use the newest, shiniest, cheapest, fastest things. Then you package those and make them available to our internal consumers or the external cloud folk. There's a bunch of abstractions that take place there. I used to be in that domain. And then people use them, if you're lucky. Actually, they tend to use them quite a lot. And then you use that to inform what the forecasts are going to be, right? So a combination of what people did, plus organic growth forecast, plus some special case extras that we know are coming. And to avoid this thing being completely open loop, you provide some back pressure to the internal product areas. Think people like cloud or maps or Google Meet or web search or things like that, right? Internally, they pay for the computation cycles and the resources they use. So, this is a way of saying don't waste them, because they cost the company real money. And you can either choose to spend your money on equipment used badly or engineers to use it well. You choose, your choice. How much do I need to build? The obvious thing to do is you look at a graph like this and go, great, let's just extrapolate. Cool, good. I'm going to project out to the delivery time and say, good, I'll order enough stuff so that when that shows up, we're great. But suppose, for the sake of discussion, that for some reason you waited a couple of months until new data came through and it did this. Now what do you do? That's a lot of computing and networking. That's a lot. Remember, a few $100 million a pop. Yes. For $30 billion over 3 years? Yes. Let's wait a little longer, see what else happens. Well, that's not quite so bad, but it's bad in a different way. That it's flatlined. That's scary. The company input revenue is flatlining. Really not a good place to be. So you don't want that. It turned out in this particular case, if you waited long enough, what you discovered was that there was a data gathering glitch in the underlying information sources. But you didn't know that at the time. But so the point I'm really trying to make here is that business forecasting, which underpins everything that we're talking about here, is one of predicting an uncertain future in the face of potentially slightly unsavory inputs, because you're not quite sure what's going on. But that's the game you play. And then the other thing you get to do is you ask, what's the cost of building too much? Well, you can calculate that fairly straightforwardly. What's the cost of not building enough? That's basically, you could potentially impact the revenue for the whole company. That's probably pretty high. So in fact, it turns out that these two things are asymmetric. That the downside cost is much higher than the upside cost. So we bias our forecasting algorithms along those lines as a result. So we look at this in terms of timeframes. There's 3 interesting ones. The one is where our internal product areas, the teams have decided, I'm going to order a pile of computers. Good, but over a few weeks ahead of time, we're going to order 10,000 machines and put them there. Great. So that's a really firm demand. We know what's going to come. Then there's sort of predictions. And I promise that next month or next year or next quarter, sort of 6 to 9 months out, I will be doing the following things. Because, you know, my revenue stream says the following, my product forecast says like this. And then beyond that, we call forecasting magic. We have a team that sort of worries about trying to think about big long-term trends. So these are the folk that worry about, you know, should we lay a new submarine cable? Should we build a new building? Should we go acquire a new land in a particular place, and we'll be able to cope with the requirements? And as you can imagine, the further out you go, the higher the uncertainties get. So what you want to do is to defer to the last possible moment the expensive choices, like actually constructing the building. Getting land is cheap compared to getting the building, which is cheap compared to filling it with stuff. So you want to defer each of those expensive choices as long as you can. When you're done, you end up with a system diagram that looks something like this. Don't worry, I'm not going to go into it. Just the point is that there's a lot of moving parts that people need to take into account when they're trying to make predictions about the future and use that information to make fairly expensive decisions. As I said earlier, a lot of what we do ends up being denominated in power, because it turns out that the power capacity is often a constraining one on how many machines can we land. So most of the conversations that take place about the long-term forecasting stuff internally is power-based. So I'm going to do a little bit of a riff on power. Feel free to ask questions as we go, by the way. We've been carbon neutral since 2007, yay, and our goal is to be carbon free by 2030. I'm actually quite proud to work for a company that cares about these things. It costs us money to do this, but it's the right thing to do, so cool. Talking of cool, one of the ways you save a lot of power is you don't waste it cooling things. So here is basically, think of it as the cost of cooling those data centers, right? We're pumping a few megawatts into a data center, and then you have to extract that heat and make sure it goes somewhere else into the atmosphere properly. Evaporative cooling is a primary use case here. How much does it cost you to do the cooling on top of the cost of actually consuming power? So this is an industry standard metric, power usage effectiveness, total watts going into the building divided by compute watts. It can never be less than 1. And a typical data center, small scale, is sort of 1.7 to 2. You know, way off the scale. I mean, it doesn't even fit on the y-axis here. So we've been down at the sort of 10 to 10% range for the cost of the cooling and stuff like that for a few years now. You know, been making it a little bit better. So sometimes my academic colleagues ask me, so how can I help make computing more cost effective? Can I do wonderful things to help make your power and cooling better? The answer is absolutely not. The best thing you can do is to write smarter software that runs faster and use less CPU cycles, because everything else is denominated by that. If you can make better, more efficient software, that's the best thing you can do for green computing by far. Everything else is sort of little tiny things you can do to help make things a bit better. So that's good news, right? So the big wins are not going to come from better cooling. Where else can we look? Well, one of the things we can do is we can try and make sure that we're using green power rather than various random bits of power. This is a picture of a green wind farm that was actually off the coast of northern Netherlands. We came into being partly because we were willing to write a long-term power purchase contract with them. So they went and they had the business case to go build this thing, and that we caused to come into the world enough power that we can cover everything that we consume in terms of our data centers. Notice I'm very careful about the phrasing of that. I'm not saying that the electrons generated here are the ones that are consumed in, say, Singapore or even Iowa. So we've now started publishing data about where do those electrons come from. This is the graph of that Iowa data center we looked at earlier. The y-axis is time. Each of these vertical lines is a day, and the y-axis is time in the day, and the x-axis is day during the year. The greenness tells you what the source was of the electricity we consumed for that data center. Solid green means it came from wind in Iowa. Turns out middle of summer, during the day, there isn't much wind, so we fall back on the local coal-fired power station. That's not great. How can we do better? This is just the way Iowa works. You can't fix Iowa, but maybe we can do something clever about the way we use the compute capacity we have. So here's one thing we can do. If you look at the sort of carbon intensity, which is sort of a fraction of the amount of carbon you generate per megawatt or hour of electricity you consume, they typically look like this during the day. I mean, Iowa would look like that in the summer, like this sort of high intensity carbon generation during the middle of the day. And at night, it's sort of a lot more wind, so we take advantage of that. So what we want to do is to take our normal workload that sort of you could imagine is sort of evenly spread across the day and squish it, move it out to either side, move it to the low carbon intensity times. So we've got some work taking place on this. There's a paper by my colleague, Hannah Radanovic, talking about how we do some of these things, and we're pushing harder on that. There's a few other things you can do, but that's one of the big things we're trying to help make come into the world. So consuming power effectively is clearly a good thing, right? So the other thing you do, by the way, if you successfully do this is you can reduce the peak power you need during the day, which means you can either pack more computers in or build less power, which is one of the expensive parts of the data center. The other thing you can do is you can make sure that the power you consume generates more computations per joule of energy than you can with regular computers. And accelerators, sort of think of as sort of plugins to computers that go faster for a given amount of energy, are one good trick for doing this. It turns out over the last few years, one of the things that's become incredibly popular is sort of machine learning, and that's basically massive matrix math. And it turns out that massive matrix math is one of the things that you could build chips for amazingly power effectively. If you look at what the trend is, the old Moore's law of everything gets faster and cheaper, and no, it's stopped, right? They're not getting faster anymore. The number of transistors per chip is still going up for a while. The speed of each of those cores that we put on the chip is not, but the trick is we can increase the number of cores we can fit on the chip drastically. And if you're willing to make trade-offs, as you can if you're doing machine learning, it's all about sort of reducing errors. If you're willing to do things like low precision computation, how about doing floating point math with 8 bits or 16 bits rather than 32 or 64? Because, you can always fix it up later in the next iteration. That consumes much less power for a given amount of computation. So we're actually internally at the state where we have more computing power in accelerators than we do in CPUs by some measure. We've been doing this for a few years. We decided, that there's GPUs from external companies. They're a good way of doing this, but we thought we could do a bit better because we knew some things about our workload that other people didn't know. So our first version came out in 2015. We call it Tensor Processing Unit because it aligns with TensorFlow, which is our workflow engine that sort of executes ML stuff. And here, pretty picture of heatsink, cool. Then we put 4 of them on a board, cool. But note the numbers here, right? Sort of 0.2 petaflops. Petaflops. These are significant amount of computation. This is, I grew up in a world where 1 MIPS, million operations per second, was a big deal. That was what the mainframe did in the computer lab in Cambridge when I was a student. Petaflops. These are big numbers. Turns out we don't just do things one at a time. As we saw earlier, we want to have a whole room full of these things. Well, we started out by just sort of taking a couple of racks. So here's actually 2 racks worth of accelerators with their compute machines on either side of them. Now we call them pods, and now they're in the 11 petaflop range, so double-digit petaflop spaces. 2 racks, good, but it turns out also that these things are now getting power dense. So our next generation, we introduced liquid cooling. What could possibly go wrong? Liquid cooling in a data center with lots of electricity running around. Yeah, great. Mostly it works, thankfully. Good engineering, yay. And now we've got pods with 8 things in them. These are in the 100 petaflop range. These are supercomputers. And we scatter these things around our data centers. We don't just buy one of them. We buy lots because it turns out that there is no limit to the amount of computation power that our machine learning people want to be able to consume. It turns out you can do even better than that, right? You can take rows of these things and you can glue them together. And we've done that. And then we've added a next generation TPU. And we're now at the exaflop range for our computation. And the fun thing is, if you're a cloud customer, you can actually rent access to some of these things. So you can run amazing computations on our tensor processing units as well from the outside, not just on the inside. This is cool. This now allows people to do kind of things that they've never been able to do before. You want to try it for a while, go do it. And then you let go, have somebody else use it. It works really well. Cool. So this helps us get much more computation out of the power we invest into our data centers, and therefore a lot of the money we invest in our data centers. So let's now just talk about closing the whole thing and putting a sort of control loop around it, because that's sort of how I presented the thing in the beginning. Here's another version of essentially the same picture I showed you. Operations is stuff actually gets consumed and used on the top left. We use that as one of the inputs of the actual usage that we see in practice to make forecasts of how much demand is going to be showing up for sort of computation power and networking and storage and access to the external networking and things like that. Those demands sort of come into planning teams, which look at it and go, if they want that on that date, I better order these things by that date using that mechanism, because otherwise we're not going to have enough. But if I wait a week, maybe I could use that other thing, which is cheaper, etc. Planners are also the people who cope with things like, COVID, all of that fiber we were going to deploy to be able to allow us to put our networking in, we can't get it. What are we going to do now? How do we prioritize the 40% or 80% or whatever it was that we wanted to be able to do that we can't we can't do everything we could wanted to do. So now the planners are basically the people where the rubber meets the road. All of that demand, hypothetical, if only we could get this, we could do the following thing. It meets but you can't. And the hard business choices of who do we support and who do we say no to come in there. Once you've done that, you go tickle the supply chain, which sort of reaches all the way back up into the manufacturing. Some of it is internal, some of it's external. We partner with lots of other people. The time horizons here we'll come back to in a minute, but the supply chain typically it delivers stuff, and then you plug it in, turn it on, and get to start using it in the operations space. Cool. Like any control system, if you're not staring at it hard, measuring everything under the sun, you can only assume it's out of control. And it turns out a lot of what I've been working on is helping people ask the right questions about what to measure and how to measure and how to report it better in a way that makes sense to folk. So that's sort of one very simple view. I mean, it really is roughly that simple, but at the high level, at the low level, hundreds of people are engaged in each of these things and so on. We're not going to dive into that level of detail, but I want to just give you one extra level of detail on story. So the time frame we're looking at, sort of one iteration around this loop, sort of 0 to 6 months. It varies a bit depending on the kind of thing you're delivering. One complication is that each of our product areas, so search and YouTube and maps and cloud, they have their own teams do demand forecasting because it's, it's based on their business. Their business is different than somebody else's business. So, the growth rate for cloud is currently running at 44% a year, which means its capacity is doubling every 2 years. Remember that exponential growth subtitle we had earlier on. Other parts of the company aren't going so fast. So aggregate, we're doing sort of in the 20-25% range of total growth. So it varies, right? And different people have different ideas about what's going to come when. These are the folk that have the the non-smooth curve data, right? We're going to launch this thing on that date, and we believe big revenue will jump or huge usage base will increase or something. So each PA does their own demand forecasting and to some extent their own planning. And then sort of back end of the planning is shared. We have a single supply chain, roughly, and we have a single operations organization. We get a lot of efficiency out of sharing our compute infrastructure across lots of different product areas. So typical computer will actually run 10 to 50 different kinds of tasks at a time, not just one thing. So we'll be mixing background batch jobs with foreground load serving stuff. That increases our efficiency quite significantly. More on that if you want to later. But there's another time frame. That was the sort of delivering stuff when you're done. But there's another time frame. But did we have enough capacity in our supply chains to get parts? Right? I'm sure we've been keeping an eye on the horror stories of car manufacturers who don't have enough chip manufacturing capacity contracts. They've fallen into we didn't order 12 to 18 months ahead of time enough bits and pieces from our upstream suppliers. So now they didn't build the factory that would allow us to grow into those things because of reasons. And now they can't deliver. Oops. So now we're constrained. If, for example, we did not pick up the phone to Samsung 12 to 18 months ahead of time and negotiate how much RAM we thought we're going to be able to buy, that's actually going to act as a cap on the number of machines we can build. Oops. So you don't want to do that. And then there's a similar kind of thing that says, you can, even if you've got the supply chain sorted, it doesn't matter if you have nowhere to put them. If you didn't build the buildings, you didn't put the power in place, if you didn't build the wide area networking and stuff, then you can't use these things. So all of these things are operating simultaneously on multiple different time horizons and interacting with one another in interesting ways, sending signals in both directions. So as you can imagine, this is an interesting problem space to operate in from an engineering perspective, which is why I kind of like it, right? It's a problem-rich environment. And the upsides are pretty good. The number was in the video was $30 billion trailing CapEx, March 2017. So that's a few years ago, how passe. 2021, we burned through 25 billion. And looking at the end of 21, we were up at the 70 billion CapEx over the trailing 3 years. Remember that exponential growth subtitle. This is the game we get to play. And it's not enough just to make it go bigger. We wanted to make it go faster, because the biggest way you can reduce the uncertainty in the forecast is to spend less time between making the decision and having the outcome. So if instead of spending, 12 months to go construct something, if you can do it in 6 months, you probably halve the amount of uncertainty, the amount of buffering you have to put in place, and therefore the amount of inventory you have to buy to cope with uncertainties, because you don't know what the forecast of that far out is going to bring you. So these big numbers multiplied by small percentage changes turn out to be high upsides in terms of impact on an engineering perspective, which is an awesome place to be. So that's basically the story. As hopefully I communicated, there's a lot of technology behind these things. This is very much a sort of skimming the surface. I do appreciate that. Happy to talk more in detail about any of the things that we can dive into. And at this scale, efficiency matters. You know, a 1% delta in a $25 billion is way above my pay scale, right? I can more than pay for myself for having a tiny dent in the kind of behavior that we see. And for those of you who still know people who are looking for jobs, yeah, we are actually hiring. Turns out hiring people is also an exponential growth game if you're trying to support the kind of growth rates that we see in the external world. But this wasn't meant to be a hiring pitch. This was just something I had lying around for the slides that I have. And that is the end of my story.